Okay, let's get started, please. Okay, let's get started, please. Okay, can anybody remind me what we were talking about at the end of class last time? What's the last thing we talked about, just to get us back in the line of the story? Yeah, James? Complete metric spaces, right? So we're talking about Cauchy sequences, right? And then we said that we saw that if you're convergent, if you have a convergent sequence, then it's Cauchy, but that the converse wasn't true, right? If you're Cauchy, you don't necessarily converge, right? And we have this definition of a complete metric space that is one in which Cauchy sequences always converge, right? So, in a complete metric space, you have an if and only if. Okay. And the last thing we showed was that if you have if X is a compact metric space, then it's complete. Okay, and that's where we finished up, right? Having a compact metric space implies completeness, and we showed that, if you recall, by taking the closures of the tails, right? So you start off with a Cauchy sequence, right? You look at the tails, and you take the closures of those guys. That gives you a nested sequence of compact sets, right? That gives you a nested sequence of compact sets. Then, by the finite intersection property, you know that there's going to be something. There's going to be some point in the intersection of that, right? Some point in the intersection of that, and then you show that it converges. That the Cauchy sequence will converge to that point. Okay, so that's where we finished up. Okay. The door should be unlocked, but okay. So just to get people, keep people's brains going, let me ask you to do an exercise to show that if you have a Cauchy sequence, then it must be bounded. Okay, that every Cauchy sequence is bounded. Okay, so think about that. You don't have to write down a rigorous proof, but at least have some idea of why that ought to be true. Right. Right. Have some intuition about it. So think about it for a minute, and then talk with each other. Okay, turn to somebody nearby and talk with them about why it ought to be true. Okay, would anybody like to tell us why that's sort of obviously true? Why is it that Cauchiness implies boundedness? Anybody? Saba, go ahead.
Because your sequence has to converge on something, and so if it was unbounded, it wouldn't really do that.
Well, it's Cauchy. You don't know it converges, right? We're not in a complete. We're not assuming a complete method space.
Everything sort of like gets closer and closer to each other, and so you can't just go off to infinity.
Okay. So Cauchy. What does Cauchiness mean? Remember, Cauchiness means that the limit. That if you look at the diameter of the tail, right? If you look at the diameter of the tail and then take the limit of this as n goes to infinity, the limit of the diameters of the tails goes to 0, right? So remember that E sub n, right? You have some sequence. Let's call it A sub n, and we're using this notation E sub n to note the set of all the points past the nth index. Okay, so this is the tail end of your sequence. Okay, right? So, right, the limit of the tails goes to 0, right? So you know that at some point the tail is going to be smaller than the diameter of the tail is going to be smaller than 1, right? In other words, your tail is going to sit in a ball of diameter 1, right? So if the tail sits right, so there's going to be some, so for some n naught, right, E sub n naught is going to be contained inside this ball of diameter 1, right? Well, so that's the tail end, and then there's only finitely many points outside, right? There's only finitely many other points, right? There's n naught minus 1 other points, right? So they might be outside the ball, but there's only finitely many of them anyway, so they're bounded, right? It can't be unbounded. Okay, so that's why Cauchiness implies boundedness. Okay. So just a remark. In Rn, that gives us the result that Cauchy implies bounded, right? Well, that gives us the result that Cauchy implies convergent, right? Because if you're Cauchy, we just saw that you're bounded, right? But if you're bounded, you live in some kind of K-cell, right? And K-cells are compact, right? So contained in a K-cell, which is compact, right? And we just saw that if you have a Cauchy sequence in a compact metric space, then you converge, right? So Cauchiness implies that Cauchiness implies in Rn, Cauchiness implies that your sequence is contained inside a compact set, which implies that it's convergent. Okay, so that's why we know that Rn is complete. Okay, everybody all right? I hope. Okay, great. Okay. So a lot of things we're going to see today. I think you've probably seen before in calculus. I don't know if it was proven to you in calculus, but if it was, maybe you're going to be a little bit bored today. Sorry, but if it wasn't, then you get to see it actually proven. Okay. So okay. So just now we saw that if you're Cauchy, then you're bounded, right? Cauchy implies bounded, and of course, convergent implies Cauchy, which implies bounded, right? Well, we could have done this directly. We could have gone directly from convergent to bounded in exactly the same way, right? But in any case, convergent implies bounded. Does bounded imply convergent? Does bounded imply convergent? No, very much no, right? Because you could have something like -1 to the n, right? It's bounded, but it's not convergent, right? It just bounces back. Okay. However, there is a case where boundedness and boundedness is equivalent to convergent, and that is monotonic sequences. Okay, so we start with with a definition. I should say that now for the time being, we're going to be in R. Okay, we're talking about increasing or decreasing sequences, and so those are we'll be talking about real numbers. This stuff had nothing to do with the numbers at all, right? This was not real numbers or complex numbers. This was just compact metric space, right? Okay, but this small interlude is in R. Okay, so let's see. So if you have a sequence Sn, a sequence in R, if Sn is less than or equal to Sn plus 1 for all n, then we call the sequence monotonically increasing. Okay, so this is what you would expect. You don't even have to write this definition down, right? It's just that the sequence is getting bigger as time goes on, right? Okay, so monotonically increasing, and if I change the direction of this inequality, then it's called monotonically decreasing. Right? Okay, and if I get rid of the equal sign here, we call it strictly increasing or strictly decreasing. Okay, so if it's this way, it's strictly. Okay. Okay. So here's the theorem that if you have, it's called the monotonic sequence theorem. That if you have a monotonic sequence, so either increasing or decreasing, whichever one, doesn't matter, then the sequence converges if and only if the sequence is bounded. Okay, so over here we said bounded doesn't imply convergent, right? So convergent implies bounded. That's always true, right? Convergent always implies bounded. Okay, so that part we don't have to worry, right? What the interesting part of this is the converse, that boundedness implies convergent. Okay, and that's the part that requires proof. So what this is saying is that, right, here's your picture. You've got this increasing sequence of real numbers, right, and it's bounded, right? There's some upper bound to the sequence. Okay, then it's got to converge. Okay, there's got to be some limit to the sequence. Okay. Okay, so what do you think we should do? What do you think it's going to converge to? How are we going to get the value to which it converges? Turn to somebody nearby and say, obviously we're going to do this. Okay, what are we going to do? what's going to be the thing we converge to? Always. Okay, would somebody like to tell me what that thing will be? What will it be? You talked a lot, but nobody's willing. Yes. Imo, go ahead.
It converges to the least upper bound.
The least upper bound, right? So it's kind of like the setup is clear. You've got a bunch of values and they're bounded above, right? Got a bunch of values, they're bounded above, so there exist a least upper bound, right? Right. So there's going to be what do we call these guys? S1, S2, S3, blah blah blah. Let S star be the least upper bound. Yeah. Okay. Yeah. That's not what I wrote in my notes, but it's okay. Let this guy be the least upper bound, and then we want to show that's we're expecting that it's going to converge to that least upper bound, right? So remember what we have to do to show convergence. We have to show that given any epsilon, there's a time past which all the values are within the epsilon neighborhood. Right? So, right? Well, we know that there's got to be one guy, right? There's got to be one guy inside the epsilon neighborhood, right? Because if there's nobody in there, then it's not the least upper bound, right? Right? So there's got to be one guy, let's call it S and naught, that's, sorry. Let's say at time n naught, that's inside there, right? And we know that everybody past there, right? So there's somebody inside there, and everybody past there is above that and lower than S star. So everybody past that is inside everybody past that is inside this little interval here, and so lies in the epsilon neighborhood. Okay, so that's the proof, right? So so let S star be the supremum of the set of values. So let's call it E1 is the set of values of the sequence. Okay. Okay. So some of these might be duplicated. So I don't want to say let it be all these points. Anyway, just a set of values without duplicates. Okay. Right. Right, we know it exists since E1 is bounded above. Right. Then we prove we claim then the Sn converges to S star for given any epsilon. We know that there exists some S n naught inside of S star minus epsilon S star. Right? For if not, S star is not the supremum. Right? But then, for all n greater than n naught, right, Sn is going to be greater than or equal to Sn is going to be greater than or equal to Sn naught, which is greater than S star minus epsilon, right? And it has to be less than or equal to S star, which is of course less than S star plus epsilon, right? So everybody lies lies in the interval of radius epsilon around S star. Right? Okay, So that does it, right? Given any epsilon, we found a time past which everybody lies inside the epsilon neighborhood of S star, right? So that's the end. Okay, everybody all right with that? Yeah. Just how do you remember how to prove that a limit, that something is a limit? Okay, everybody all right? Any questions? Okay, let's go on. So I said that most of this stuff would be, or a lot of this stuff would be stuff that you've seen before, but actually that's not true. Right now we're going to do something you've probably never seen before. Okay, so limit superior and limit inferior. Okay, which people usually abbreviate lim sup and lim inf. It's also abbreviated lim with a bar above it, or lim with a bar below it. Okay. So these are basically refinements, or no, generalizations of the limit. So these are things, so if you recall back in Calculus 2 or whenever, you had all these tests like ratio test, root test, all those tests for convergence of series. You may recall that those hinged on the existence of certain limits, right? If this limit is bigger than 1, then the thing diverges. If the limit is less than 1, then the thing converges, right? This sort of thing. You remember this? I don't know. Maybe that's a long time ago for you. Okay. The trouble with that is that those limits may not exist. Okay. The good thing is that these limits, or rather the lim sup, all of those tests can be phrased in terms of the lim sup. Okay. And the lim sup always exists. Okay, so it basically gives you a more powerful version of the tests that you had before. Okay. Okay, so let's get to it. First off, just a notation, basically. Okay, so the notation is what we mean by convergence to infinity. Sn goes to infinity, or Sn goes to negative infinity. Okay, so if you have a sequence of real numbers, and if for all m, for all natural numbers, no, it doesn't matter, for all real numbers, say, there exists there exists a time such that Sn is bigger than m for all n bigger than n. Then we write Sn converges to infinity. Okay, and then similarly for negative infinity, right? So the picture you want to have here is that you've got this sequence, and it's bouncing around and whatever, but no matter what bar you set it, there is some time, and that time depends on the bar, on the height of the bar, right? Past which all values exceed that bar. Okay, so if I say I'm going to set a bar, my sequence goes to infinity that should mean that if I say I want everybody to be bigger than 1 billion, there's a time past which all values are bigger than 1 billion, right? Right. That ought to be true if your sequence converges to infinity, right? So if I say, okay, how about 1 trillion, right? How about 1 trillion? Is there a place past which the thing, right? And there should be another place past which everybody is bigger than 1 trillion, and so on and so forth. So no matter what bar is given, there's always a point past which everybody jumps over that bar. Okay, and of course, if you're talking the other way, there would be a place where everybody's below the bar. Okay, so that's called converging to infinity. Sometimes that's considered diverging, but we're going to consider it as converging. In what follows. Okay. So now we get to the real definition. A more interesting definition. So again, we start off with a sequence of real numbers. Okay. And we let E denote the set of all subsequential limits. Of Sn. Okay, so this is a little bit of a funny thing, right? You have your sequence, and then you look at all the subsequences, right? All possible subsequences. And you say, okay, let's look at whatever limits there are of those subsequences. Okay. All of those, you take all those limits of subsequences and you put them in a set and call that E. Okay. So that's the sequence, the set of subsequential limits. Okay, so for kind of a dumb example, if we have Sn being -1 to the n, right, then there's no limit to this. There's no limit to this sequence. But you can make subsequences that converge, right? You can make one subsequence that, you can make subsequences that converge to 1, and you can make subsequences that converge to -1, right? By taking, for example, the odd terms or the even terms, right? So in this case, E would be -1 and +1, right? Those would be the subsequential limits for this thing. Okay, this is the set of subsequential limits. Here's your sequence. You look at all the subsequences, and these are the only limits of those subsequences. Okay. Okay. So you have the set of all subsequential limits, and notice that this E is a subset of the extended real numbers. Right? You could have -infinity or +infinity in it, right? Because you might have some subsequence that converges to some positive or negative infinity. Okay. Then we define the lim sup of E as the supremum of E. Sorry, the lim sup not of E, the lim sup of the sequence. Sorry, the lim sup of the sequence is defined to be the supremum of the set of subsequential limits. Okay, that might be infinity, or it could be that number exists, right? It might be infinity. If it's not infinity, then it's some finite number. Okay, but whatever, you're always going to have something, infinite or finite. You're guaranteed that this thing is going to exist. Okay. Okay, and similarly for lim_inf, although lim_inf is not really going to be used so much for us. Lim_inf is going to be the infi one of the set of subsequential limits. And so in this example, for the lim sup of this, is 1, and the lim_inf of this sequence is -1. Okay, so notice that lim sup and lim_inf always exist. Unlike limits, these things always exist. Okay. Let's see. So I have a question for you. Is E the set of all subsequential limits closed? What do you think? Is the set of subsequential limits closed? So these guys are in E, right? Let's suppose that it's finite for now. Then there's going to be a supremum of E, right? Which we call S star. Okay, so like there's these guys are all in E, so. Right, there's a supremum. Is that going to be, is the supremum of the set of subsequential limits itself a subsequential limit? Turn to a partner and talk for a minute or so. Okay, who thinks it's true? It's closed? Anybody think it's closed? Who thinks it's not closed? most people are not, don't dare to venture an answer. That's okay. You guys who ventured answers are brave. The answer is yes. The answer is yes. Actually, it is closed. So whenever you have a limit, whenever you have a limit point of the, right? If you have a limit point of the, yeah, what am I doing here? This is actually not what we want to think about. This is the wrong picture entirely, right? we're not looking at the supremum. We're looking at some limit point, right? So let P be a limit point of E, right? So P is in E prime. Okay, right? And we're hoping that that guy is going to be, in fact, the limit of a subsequence, right? Okay, and I'm not gonna do the proof carefully, but you can kind of see what you would need to do. You would say, okay, so we want to construct. Right? We want to construct a subsequence of Sn that converges to P. Right? So the first thing you do, you just start off with anybody. Right? So just pick some point, S1 or something like that. Right? So pick some point S1, right? That's not equal to P. If they're all equal to P, then you're done, of course. Assume that they're not all equal to P. Choose one guy that isn't. Let's say it's Sn1. Okay. So this guy is not equal to P, right? Right. And then use that distance as your first epsilon. Right. So let epsilon 1 be the distance from Sn1 to P. And maybe let's say divided by 2. Okay, so we'll take half of that. Half of that distance. Okay. Right? Now, so here's plus epsilon 1 minus epsilon 1. Okay. Now this guy is the limit point of E, right? So we know that right, it's the limit point of the set of subsequential limits. So we know that there's a subsequential limit somewhere inside here, right? So we know that there's some subsequential limit. Let's call it E1, right? There exists some E1 that's in E that lies inside of that epsilon neighborhood of P. Right? Right? Because this is the limit point. Right? So there's got to be somebody inside there, somebody from E that's inside there. Right? But this guy is a subsequential limit. Right? So there's some subsequence that converges to that guy. Right? So we can choose Sn2 where N2 is bigger than N1. And the distance of Sn2 to E1 is less than epsilon 1, say. Okay. I probably need to put in some halves or something like that to make this work out. But you see what's going to happen, right? So you know that there's going to be you know that there's going to be some SN2 close to this E1, and so it's close to P, right? And then you just keep on going that way, right? So you just say, okay, now take that guy as to create your epsilon 2. You take that guy to create your epsilon 2, right? And then take that thing, use that to create a new epsilon, right? That's smaller, right? And then you choose there's going to be some E2 inside here, right? There's going to be some Sn3 that's closer, and so on and so forth. And in that way, you construct your sequence that converges to P. Okay. So in any case, E is closed. Okay. 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 So, yeah. not going to say more than that. Okay. So what we're going to prove now is a characterization of the limb soup. So okay, so it's like a way of thinking, another way of thinking about the limb soup. There are multiple ways of thinking about the limb soup. You know, one, the way we defined it is just the supremum of the set of subsequential limits, right? Here's another way of defining the limb soup. There's another third way that's popular. I think that will be put in the exercises to show that that's equivalent. Okay. Okay, so here we go. We have a sequence, and E, the set of subsequential limits. Okay, then one, the limb soup actually is a subsequential limit itself. Okay, so limb soup is a subsequential limit, and two, given any x bigger than the limb soup, there exists a time such that past that time, all values of s are smaller than x. Okay. But doesn't matter, it's strictly smaller than this. Okay. Further, any number satisfying 1 and 2 must be the limb soup. Okay, so, right, so the limb soup has these properties, and in fact, these properties characterize the limb soup, right? If you have these properties, that means you are the limb soup. So that's why we call it a characterization, right? It specifies the limb soup exactly. It's not just a description, but right, anybody that satisfies those qualities has to be the limb soup. There's only the limb soup does that. Okay, everybody all right? Okay, this is sorry, this is not the most interesting stuff, and so just bear with it, and we will get to more. No, it's all, the rest of the class is not that interesting. Okay, but okay, anyway. So we'll get to more interesting stuff later. I'm not sure how much later. I mean, definitely by the end of the semester, we'll have some really amazing results. Okay, we have to slog through some of the boring stuff, but that's just life, right? Sometimes you need to go through the boring stuff. Okay. Okay. So this first one we have to be a little bit careful because there's the possibility that that the limb soup is infinite. Okay, so let S star denote the limb soup of Sn. Okay, right. So it's the in other words the supremum V. Right. So case one. suppose that's infinite. Okay. Right. In that case, right. In that case, E is not bounded above. Right. And so that implies that the sequence Sn is not bounded above. Right. And that implies that there exists a subsequence converging to infinity. Right? If there's no upper bound on the set of subsequential limits, well then your sequence itself must not have an upper bound. Right? But if your sequence doesn't have an upper bound, then you can construct a subsequence that converges to infinity. Right? Okay, so infinity, so then S star actually is in E. Okay. Next one. Maybe I should try to go faster. If S star is negative infinity, well, what would that mean? If S star is negative infinity, that tells us that the supremum of the set of subsequential limits is negative infinity. Right? What does that tell you? Right? That would tell you that E is just negative infinity. Right? Right? There's only one. Right? This would be the, and in that case, negative infinity is in there. Right? So that's the right? So then again, S star is in E. Okay. So those are the infinite cases. The finite case. Right? So we may assume, of course, without loss of generality, we may assume that no, sorry. So in this last case, right, the supremum E is a limit point of the subsequential limits, right? Right. No, actually, we do have this. So suppose that S star is not in E. Okay. But in that case, the supremum is a limit point of E, and that implies that it's contained in E. Right? Because since E is closed, then supremum E must be in E itself. So we get a contradiction. So if S star is not in there, then we get a contradiction. So S star must be in E. Okay. Okay. Is everybody all right? Sorry, let me, okay, do you guys want to just read this part on your own, or should I do it, or do you want to read this part on your own? It's not particularly exciting. We can, let me finish it. I'm sorry. I'll finish it. Okay. Part 2. Given any x bigger than the lim sup, there must be a time. So you have your sequence. Here's the lim sup. Here's the lim sup of your sequence. And what it's saying is that given anything bigger than that, there's a time past which everybody is below there. Okay. There's a time past which everybody is below there. Okay. And for the lim inf, right? The lim inf, what it's saying is that, given anything smaller than that, then there's a time past which everything is above there. Okay. Let me ask you this: what if the lim sup equals the lim inf? No.
Does it converge?
Then you'd have then this would actually be the limit, right? Because then you'd have the single point with the property that you can find given anything above, you can find a time past which everything is below that, and you can do the same thing on the opposite side. So suppose there were one guy where the lim inf equaled the lim sup. That would mean that you can take a value above and you can take a value below, and there's some time past which you lie within those bars. Well, that's the notion of limit, right? So these are sort of like half. Each of these is sort of half of the properties of the limit. Okay, and if they're equal to each other, then you actually have a limit. Okay. So okay. So we're trying to show that that given any x bigger than lim sup s sub n, there exists a time such that if you pass that time, then s is less than x. Okay. So suppose that suppose that doesn't happen. Okay, suppose that doesn't happen, right? That you can't find this n that works for it, right? Okay. Suppose that for all n, there is no n that works, right? There's an n bigger than an n such that Sn exceeds x. Okay. Right? So suppose all of the n fail. Right? Well, in that case, Sn would be bigger than x for infinitely many indices n. Right? But in that case, the set of subsequential limits will contain some value bigger than x. Right? Because you're going to have infinitely many values that are bigger than x, and so you can construct. It could be possibly infinite. Right? You could construct a sequence. You could construct a subsequence that converges to something bigger than x, right? Because you've got infinitely many of them. Okay, so that's why you have this half limit property here. Okay, I think that's all I want to say about lim sup and lim inf. Like I said, these will be important because we'll be using them in convergence tests for series. Okay. Okay, so let me, so I'll let you read this last part by yourself, right? That any number satisfying 1 and 2 must be the lim sup. Okay, so now we're going to go on to series. Oops. Okay, so now we're going to go on to series. Okay, so infinite series of complex numbers. Okay, so again, this is stuff that you've probably seen before, but I doubt you'll have seen how we're gonna explain it. Okay, so first off, some notation. Right, you have a sequence, A sub n, a sequence of complex numbers. Okay, and we let summation A sub n from n equals p to q be AP plus AP plus 1 plus AQ. Okay, so I'm sure you've seen this sort of notation before, right? This is just the summation notation, right? So you're summing the A sub n's from P to Q, right? So go from AP to AQ. Okay. You have, again, a sequence. Then we define the sequence of partial sums. Of A sub n is defined as the sum as a sequence, so let's call it sequence S sub n of partial sums is the sequence you get by summing the terms from 1 to n, right, of the A's. Okay. Right. I assume you've seen this sort of thing, right? So you have, so for example, right, if A sub n is 1 over n, right, then S1 is going to be, right, so A sub n, the A sub, right, so this is going to be, 1, 1/2, 1/3, 1/4, etc. Right? Then S1 is the sum of the first term only. S2 is the sum of the first 2 terms. S3 is the sum of the first three terms. Right? And so on and so forth. Right? So these, for every sequence, there's going to be a corresponding sequence of partial sums. Okay, right. So you've got sequences of partial sums. Okay, and if the sequence of partial sums converges, to some S, then we write that the infinite series converges to S, right? S n goes from 1 to infinity. Right? And say the infinite series converges to S. Okay, so this, you think of that maybe we're adding an infinite number of numbers here. That's actually not the case, right? What we're doing is looking at the convergence of the sequence of partial sums. Okay. Okay, so right, whenever you see something like this, you want to think, okay, what this is saying is that the sequence of partial sums converges to S, right? That if you look at the sequence of partial sums from that this limit equals X. That's really what that means, right? This is just a notation for this reality here. Okay. 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 So we're going to give you something called the Cauchy Criterion for convergence of infinite series. Okay. So a series converges, and this is very, very useful. Okay. It's not something that you use to actually evaluate convergence of a series, but it's useful theoretically. Okay. So you wouldn't take a series and say, okay, I'm going to apply the Cauchy criterion to it to actually check if it converged, but it's useful theoretically. So a series converges if and only if for all epsilon greater than 0, there exists an n such that the size of, such that for all m and n bigger than n, the size of the tail from k equals m to n, or I have an n to m in my notes. From n to m is smaller than epsilon. Okay. 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 So the proof of this is just to use Cauchiness. Okay. So it's just this is actually not anything deep. You say, okay, well, let's think this thing converges. That means that the sequence of partial sums converges. Right? Sequence of partial sums. Right? That's just by definition. Right? Okay. And then let's right. This is convergence can be thought of, because we're in the complex numbers or the real numbers, whichever. Those spaces are complete, and so we know that convergence is equivalent to being Cauchy. Okay, so this thing is Cauchy. Okay, well, what does Cauchy mean? Cauchy means that you can make points close to each other, right? So given any epsilon, there exists an n such that whenever you take two values past that n, Sn minus Sm is smaller than epsilon. Right? That's what that means. But that's basically, let's translate that to this in terms of A. So let's say that say n m is bigger than n. Okay. Well, what does that mean? That means that the partial sum. I'll just rewrite this as m minus n. The partial sum up to m of the AKs minus the partial sum up to n is smaller than epsilon. Right? But what's this? This is going to be that's just the sum from n plus k equals n plus 1 to m of a sub k is smaller than epsilon. Okay, which is basically this. Okay, so this Cauchy criterion is just a translation of the partial sum sequence being Cauchy. Right. 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 That's basically the proof here. Right. S sub n is Cauchy. Give more detail in your own homework than this, but yeah, that's basically the essence. If I may try to liven things up with a story, when I was an undergraduate at Princeton, there was this one student who everybody recognized was like a genius beyond geniuses. Like he finished his undergraduate degree in 3 years, and I think. So, and then he was admitted to the graduate school, which never happens. In math graduate schools, in math schools, you never accept to graduate school your undergraduates. You generally just send them out to some other graduate school. I'm not sure why. It's just to have them, go abroad basically, get some different experience other than their own institution. But in his case, he was accepted to Princeton for graduate school, and I was told he finished his degree, his PhD, in 1 year. Okay, so smart guy. The story that we heard about him was that, so of course, the homeworks were really long and horrible, but we heard that. What I heard was that this guy would turn in homeworks that would say, "This is obvious," and right, so his answer would be, "This is obvious." And the grader would be like, full points for you. Right? Because they knew that for this guy, it was obvious. So.
So I'm going to get full points now on everything?
Yeah, so yeah. Yeah. So if you're curious about what happened to this guy, look up ABC conjecture. Okay, so that'll lead you to it. Okay, okay. So infinite series, right? Infinite series. We have this thing. A series converges means that you can make the tail as small as you want, right? Given any epsilon, there's a time past which the chopped off pieces of the tail are as small as you want, right? And you notice that actually says that you can let m go to infinity. So if that actually makes any sense, then it's got to be less than epsilon also. So in other words, being for the series to converge means that you can make the tail as small as you want. Okay, that's how you want to think about convergence. Just one remark here. Notice that if I take, right, we're saying that for all m and n bigger than n, it's going to be less than epsilon. What if I take m equal to n? What would that tell me? That would tell me that one value is less than epsilon, right? The magnitude of that single a sub m is less than epsilon. Right, so given any epsilon, there's a time past which the size of the value is less than epsilon, right? What does that tell you about the sequence?
Is it a single point?
No. The sequence converges to. Let me write it out. So notice that what we have here is that. So if a sub n series converges, then we have that for any epsilon greater than 0, there's just a time such that past that time, A sub n is smaller than epsilon. What did I tell you about the sequence A sub n? Converges to 0. Right? Given any epsilon, there's a time past which the values are smaller than epsilon. Right? That's exactly saying that the limit of the A sub n is 0. Right? This is something you saw called the divergence test, maybe, or the nth term test. Right? If it converges, then your values must, if your series converges, then your sequence goes to 0. Right? Or conversely, if your sequence doesn't go to 0, right, contrapositively, if your sequence doesn't go to 0, then your series must diverge. Right? So contrapositive, right, if the limit of A sub n is not 0, then the series must diverge. Okay. I'll do one more. One or two more things. Okay. So okay. So one. So a theorem about non-negative series. So if A sub n is non-negative, okay, so suppose you have a bunch of non-negative numbers, and you're looking at the series. Okay. So this thing converges if and only if the sequence of partial sums is bounded. Okay, maybe we'll stop with this one since, I think everybody's at their limit. Yeah, so why does that make sense? Right? So you know that this thing converges means that this thing converges, right? Right. This thing converges means that this thing converges, right? That's just the definition. I'll put a D, a capital D there for definition. Okay. Okay. Further. So why should that be if and only if this is bounded? Well, because this thing is a non-negative, these guys are non-negative, right? The S of n is a monotonic sequence, monotonic increasing sequence, right? It's a monotonic increasing sequence, so you know that convergence is equivalent to being bounded, right? That was the monotonic sequence thing we did before. Okay. Okay, that's it for today. Sorry that a lot of that was not the most fun. Next time, guaranteed more fun.